So just like we talked about with double integrals, sometimes they're easier to do in polar. Triple integrals are sometimes easier to do in cylindrical or spherical, which are coordinate systems we looked at earlier this semester. So we're just going to very quickly review those and then look at a couple of examples. So first off, we'll talk about cylindrical, because cylindrical is a little bit more where we already have some familiarity with it, because it's basically polar plus the z-axis. All right. So if you remember, we talked about this. It was a long time ago. It was before the midterm, back in module 2. So to identify a point in cylindrical, r and theta are in the xy plane, and then z takes us above the xy plane, just like it does in Cartesian. So it's the same exact z coordinate. So we have our conversions: x equals r cosine theta, y equals r sine theta, z equals z. All right, and I don't have them on the slide here, but just as another reminder, r squared equals x squared plus y squared, and tangent of theta equals y over x. Okay, those were our conversions for polar. All of those still hold for cylindrical. So let's go over this. We did this exact exercise when we saw these last time, but it's worth going over again. So we need to think about what kind of surface we get if r is equal to a constant. Okay, so let's go back to here. So if r is set as a constant, what kind of surface are we going to get in 3D? It's going to be a cylinder, hence the name cylindrical coordinates. It won't be a sphere because r is stuck in the xy plane. It just goes around in the xy plane. So it forms a circle in the xy plane as theta goes up and down, and then z makes that circle go up and down, which creates the cylinder. Okay. What about if theta is a constant? Let's go back to our thing. So now theta is a constant. So this part here is constant. R can vary and z can. It is going to be a plane along r and z. So it's going to go through the z-axis, right? It's going to be parallel to the z-axis and perpendicular to the xy plane. So that's if theta is a constant. Lastly, what if z is a constant? So z is our height above the xy plane. So if we set z to be a constant, we have what? To the z-axis or parallel to the xy plane, right? So these are what we call our fundamental surfaces. And so if you have regions, so remember, we're looking at these 3D regions now, right? If you have regions that are combinations of these fundamental surfaces, cylinder, a plane that goes through the z-axis perpendicular to the xy plane, or a plane parallel to the xy plane, that would be our hint that we might want to use cylindrical, because it'd be very easy to use constants for our bounds. So that's the kind of thing you want to look for. And that's why we talk about these fundamental surfaces. So that's how we would look for using cylindrical. And remember in polar that the dA had that extra r in there. And one of the things you're going to see when you do the section 14.8 for Tuesday, you're going to see how this is actually calculated. But we saw, we talked about it, it's been talked about a little bit more intuitively. So in rectangular, we still have to add that r, excuse me, for a triple integral in cylindrical, we still have to add that r just like we did in polar, okay? So that has to be part of our dv. So if you convert to polar to do your integral, remember to put that extra r in there. All right. So we're not going to do that just yet. Spherical coordinates. So we looked at these before too. So spherical are in terms of rho, which is that P looking letter, phi, which is the circle with the line through it, and theta. Rho is the distance from the origin. So now rho is no longer stuck in the XY plane. It can go up, down, anywhere in 3D space, but it's always the distance from the origin. Phi is the angle that is made with the positive Z axis. Okay, and phi will bound in between 0 and pi. We'll only take it from the positive Z axis to the negative Z axis. We won't go any further because we can always rotate around with theta. We don't want to double count stuff. So phi takes rho up and down. And finally, theta is the exact same theta that it was in polar. Okay. Now the transformations, as we saw back in module 2, are more complex, right? There's a lot more going on, and it's because we're in 3 space. It is still all right angle trig, but as we've talked about before, do not worry about memorizing these. These are things that can go on your note card. What we need to know is how to use them. All right. Let's talk about the fundamental surfaces for spherical. So if rho is a constant, so rho being the distance from the origin, so if rho is a constant and phi and theta are allowed to vary, what are we going to get? It's going to be more than a line, because so what you want to think about this line here being the same length. So phi is going to vary. It's going to take it around here, and then theta will be a sphere. Hence the name spherical coordinates. So if rho is a constant, it'll be a sphere. The other way we could recognize it, look at the equation for rho. It's the equation of a sphere, right? X squared plus y squared plus z squared is a sphere centered at 0, 0, 0 with a radius of rho. All right, theta being constant, actually it's the same theta as before, so it's the same plane as before, right? It's still that plane that is going to go through the z-axis that's perpendicular to the xy plane. So again, that would be a surface we'd look for. So a hemisphere would be really easy to do in spherical, or quarter sphere, or an eighth of a sphere, right? Like if you kind of can imagine like a wedge of a sphere. We could do that very easily with constants in spherical. Okay, last one. If phi is a constant, so let's go back and look at what phi is. So now this guy here, the angle between z and rho is now constant. But this thing can be spun around this way, and it can be lengthened out this way. This will be our cone. So spherical is very good for dealing with cones as well. All right. What we would need to know is what is the angle on the cone. Questions about that? So again, those are our fundamental surfaces. We go through those because that's when we're going to say, hey, spherical will be the easiest. All right. And what we're going to look at, we're going to do a couple of examples here in a minute. And we'll see how many different coordinate systems we can do them in, and what looks good and what looks bad as far as actually having to calculate. One last thing we do need to talk about, though, is the dV for spherical coordinates. So you know how you have to put in the R for cylindrical? There's a piece we need to put in for spherical as well. Do not memorize this piece, have it on your note card, but do not forget it, because without it, your integral will be wrong. So your dV has to include a rho squared sine phi. All right. And then the order is whatever order is most advantageous. Now you saw this in the video, but just to kind of see where this comes from, this is what we're integrating over in spherical. All right. So delta phi is easy to see, right? It's just the delta rho is easy. It's just the change in rho. But to get these other sides, for instance, to get this side here, this is an arc length. So it needs to be the radius times the angle. So that's where the rho delta phi comes from. So that puts in one of the rows is this arc length here. This is also an arc length because it's spherical in this direction. So to get this arc length, it's going to be rho sine phi because we have to get the appropriate row in there. Excuse me, the appropriate radius in there. And then delta theta is our angle going this way. So multiplying these three elements together, that's where we get the rho times rho for the rho squared. That's where the sine phi comes from. And then our three deltas. Again, you don't need to memorize that. I just wanted to kind of give you a little bit of an idea where it comes from. It's not made up. It's not arbitrary. We'll see how we calculate it with the Jacobian in 14.8. But the big thing the big takeaway is that anytime you do an integral in spherical, you have to put in a rho squared sine phi into your integrand along with whatever else is already in there. Okay. I'll leave the first four. We're going to look at 5 and 6. So first off, let's look at 5. Okay. So we can always put these in calcplot 3D if we're not sure what they look like. So if I'm looking at number 5 here, I've got the hemisphere. So square root of 8 minus x squared minus y squared. All right, so that's creating the top here. And let's add in the cone. That's just going to be square root of x squared plus y squared. Now, we could adjust this to make it look nicer, but I think we can all see the volume that's being enclosed there, right? We're not worried about these little flanges hanging off. So let's talk about setting up a triple integral for this guy. Now, I think from the image, I think we see a clear top and bottom, right? Let's start off in rectangular, then we'll talk about other coordinate systems. So right off the bat, that hemisphere is on top, the cone's on bottom. So let's start setting this thing up in rectangular. Cone's on bottom. And so we're okay there, right? This is the best part because now we're out of 3D and we're into 2D. We got the hardest part taken care of. So that's going to be our DZ. And I'm just going to be setting these up. I'm not going to be calculating them. We can use Wolfram to calculate. I'm going to encourage you guys to do the same thing today. Focus on setting up because I want you to try and do multiple systems if you can. Some of them aren't going to be easy to do in multiple systems and some will. Okay, so now we're in the XY plane. And remember we talked about the shadow region, right? Which is going to be the intersection of these two. Which is this region right here, which is basically a circle created by the intersection. So what we need to figure out is what that circle looks like in the XY plane. What's its radius? If we know its radius, we're in good shape because we've done so many times over now a region of a circle in the XY plane. So all we really need is the radius, and we're going to get that by looking at the intersection of the two by setting them equal to each other. Okay, so we square both sides to get rid of the radicals. And we're just going to put this into the form of a circle. So I'll bring the x squared and the y squared over. So 2x squared plus 2y squared. This one might look a little familiar from last time. So x squared plus y squared equals 4. I'm dividing everything by 2. So that tells me in the xy plane, I've basically got a circle of radius 2. Well, we know how to handle that. So circle of radius 2 is going to go from negative square root of 4 minus, we can do x or y on this one. Let's just do, we'll put x squared here. 4 minus x squared. So I'm doing x, or excuse me, dy next. And then lastly, negative 2 to 2 for our radius, right? I know I didn't spend a lot of time on that, but again, that's one we've seen before. We should be getting good at doing a circle in the XY plane for limits. But questions about that setup so far? it's set up correctly, probably not going to be a lot of fun to calculate. What do you already think is going to be an easier system to use? Probably cylindrical because of the circle, right? The circle just cries out cylindrical. Now here's how easy this is to change to cylindrical. Remember, x squared plus y squared is r squared, right? So this lower limit becomes the square root of r squared, which just becomes r. So that's actually, and remember, that was one of our fundamental surfaces, right? If, well, actually, the cone wasn't for cylindrical, so we'll talk about that in a second. So there's our r. Here, we have an x squared plus y squared because I can factor the negative out of there, right? So I can rewrite that as 8 minus the quantity x squared plus y squared. So what's the upper limit going to become? Square root of 8 minus r squared. Now this is still dz, and like we said, we're switching to cylindrical, so we do have to put the r in there. So all that stays like that, right? Now here's where it gets even easier. All we're doing now is we're now into polar, right? And doing a circle of radius 2. So if we did, let's say r next, r is going to go from 0 to 2. And that leaves us with theta last. That we have to take it all the way around the circle. 0 to 2 pi. Very good. Significantly easier from a calculational standpoint than this one, right? Both correct, but this one's going to be easier. Okay. Now, the one we haven't had as much practice with, spherical. Think about what my surfaces are here. On top, I have a sphere, hence the name spherical. We knew that was a fundamental surface. And on bottom, I have a cone. Remember, we said cone was a fundamental surface for spherical also. So this is basically two fundamental surfaces put together for spherical. So most likely, spherical is going to be the easiest. But let's talk about how we set up spherical. I always like to start with rho. And since I'm going to spherical, I do need the rho squared sine phi in there. I'm just going to put that in there. Be done with it. Okay. Now, rho, remember what it does. It goes from the origin out to the edge of this surface, right? And it's already a sphere, which means rho gets to be a constant. So rho is going to go from 0 out to whatever the radius of the sphere is. What is the radius of our sphere? 2. Not quite. That was the radius of this circle where they intersected. So let's go back to what created the sphere, right? It was this function here, z equals square root of 8 minus x squared minus y squared. Here's a very easy way to find the radius. What if x and y are 0? That would put us out at the radius. What would we have? Square root of 8. So we got to be careful, right? There's two different radii going on, and that's one of the things we have to pay attention to. There's the radius of the circle of intersection, which we needed in order to get that xy plane. But now we're talking about the sphere itself. We haven't had to deal with the radius of the sphere yet, really. So square root of 8, or if you want 2 rad 2 is fine as well. Okay. So what that's going to do is that's going to basically make a line that goes from the origin out to the edge of the sphere. Now phi, we need to rotate and start to sweep out the top of the sphere there. And then theta will rotate it around. Does that make sense? Yes, we should put that on there. Yep. Okay, let's talk about phi next. Remember, if phi is a constant, that's where it creates a cone. So we have this situation. Let's look straight down this side. We have a cone, and then we have this basic dome here, right? That is phi. So phi, we're going to do phi next, is going to start at 0 and then go out to the edge of this cone. Okay. So that means we need to have an idea of what the angle is on this cone. There's a couple different ways we can approach this. Number one is we can go straight up the equation. Right? Now I'm kind of, I'm going to put on, I'm going to use a different color for this. Hopefully it shows up at home. X and Z. We can pretend we're in the XZ plane for right now. And in other words, we're going to set y equal to 0. So remember that the cone was made by square root of x squared plus y squared. But we're setting y to 0. So z equals square root of x squared, or z equals x. Now, the reason that's important, that tells us that this is a 45-degree line. So phi is going to be pi over 4. There are other ways to do this. We could look at what this intersection point is, right? Create a right triangle and figure out the angle. I don't know why I did that. Thank you. Pi over 4. There's other way that would be the other way we could do it, especially if it was one that wasn't as obvious, right? This one, by looking at the trace, we can say, oh, that's a 45-degree line, no problem. But if we weren't sure, find this intersection point in the XY plane and drop down, make a right triangle and find your angle. So what that does is create this piece here, and then to get the whole cone, theta rotates it around the z-axis. And it's, again, the same theta that we used before. So 0 to 2 pi. All three of these will result in the same answer. If you had to calculate it by hand, which one would you want to use? Most likely the bottom one, because all of our limits are constants, which means we can do this literally in any order we want. This one is going to be probably, not even probably, this will be the easiest to do by hand. This one probably won't be too bad. We can do a u sub on that, and we'll have an r squared in there. And then the rest are constants. This won't be a bad one by hand. No. This one we don't want to do by hand. That one would be a mess. And that's why we have these different coordinate systems, even though all three of them give the exact same result. Okay, questions about this one? All right, then let's do one more, and then I'm going to cut you guys loose on some, because it's really all we can do is practice them. We're going to go to number 6. Number 6 is an interesting one that I want to show you some stuff on. And we'll talk again about that phi angle, because that'll come up again. So take a look at number 6 there. Okay, so in this one, I'm not going to plot this one, but we've got a cylinder inside a sphere, and we want the region outside the cylinder and inside the sphere. So let's just give, let's give a side view of what's going on here. So we've got this sphere of radius rad 2, and then a cylinder cutting through it. Okay, so that part is being eliminated, and we've got this region here, and it's kind of going around the cylinder, right? It's like if you had a tennis ball and you put a cylindrical pipe through it, right? You can kind of imagine that shape, and what would be left of the tennis ball is our region. Okay, so let's start to talk about the options here. So first off, and now this time we are integrating over a function. Not a big deal. Again, the biggest part is always going to be figuring out the limits. Now, if we wanted to do rectangular. Rectangular is once again going to be the hardest because look at what our two surfaces are. We've got a sphere and we've got a cylinder. Sphere tells us spherical. Cylinder tells us cylindrical. We have no rectangular surfaces in this one. So we could do rectangular. What we would do is, and it wouldn't be pretty either, we would calculate the whole sphere, and then we would remove the cylindrical part with a spherical top and bottom. Does that make sense? It's doable, but we'd have to do two integrals. So what that would look like is, find a darker color. Let's talk about a little bit about what that would look like. This is not the way we would want to do it, but so we go from the bottom of the sphere. So negative square root, let's just do it in Z, up to positive square root of 2 minus x squared minus y squared, and we've got our function in here, x squared plus y squared, dz. Okay, so we're just doing the whole sphere. Now, once we've got the top and the bottom, it's just a circle of radius rad2 in the xy plane. So negative square root of 2 minus x squared to square root of 2 minus x squared. And then negative square root of 2 to square root of 2. Okay, dy, dx. Now we need to take out the cylinder part, right? Now here's where it gets kind of interesting. So let's think about what happens here. So minus, I like to start with the inside limits. So I need to subtract out this thing here, which has a top and bottom that is actually still the same sphere. So the inside limits look the same. Minus square root of 2 minus x squared minus y squared. And square root of 2 minus x squared minus y squared. Let's throw in our function, x squared plus y squared. And we're doing dz first as well. So what we're doing now is removing the extra that we calculated. And because we're doing it over the same function, this is actually a fine way of doing this. Okay, now our region in the xy plane is a circle of radius 1 because it's the cylinder. So circle of radius 1, so negative square root of 1 minus x squared to square root of 1 minus x squared for our dy, and negative 1 to 1 for our dx. Okay. Not something we're really going to be excited about doing by hand, right? Actually, it might even come out kind of messy on the computer, but it can be done. All right. Right. Yeah, this one's a bit of a mess. So let's talk about doing it in cylindrical, because the advantage of cylindrical is that cylindrical and spherical will allow us to do it as a single integral. And here's why. So, first thing we need to think about is what is happening with z, right? So let's kind of redo our drawing here. Well, z has a definite top and a bottom. It's still this sphere, right? Except the sphere will now be in cylindrical coordinates instead of rectangular. So our lower limit is going to be negative square root of 2 minus r squared up to square root of 2 minus r squared. Okay, that's taking us from this bottom to this top. Now we'll handle the fact that it's outside the cylinder and inside the sphere in the next step, because that's going to be our shadow region in the xy plane. But before we do, we got to do our function. Well, x squared plus y squared equals r squared from our conversions. We have to put in our extra r from our converting to polar. And then we're starting with z. Yep. Yeah, definitely multiply those together before we do any integration, right? Now, let's look straight down into the XY plane. So here's X, here's Y. Remember, this was looking at Z, and this could have been X or Y. Now we're looking straight down. We have a circle and a circle, right? Like a washer type looking thing. And so now R needs to go from the little circle out to the big circle. Not a big deal for R because it's just a radius of the cylinder, which is a radius of 1, out to rad 2. So 1 to square root of 2, and then theta will take us around. Much easier, right, than rectangular. I think we'll all agree on that. Questions about that setup? Okay, let's talk about doing it in spherical. There's an interesting thing that goes on in spherical that I want you to see. Again, we're kind of stuck in between cylindrical and spherical on this one. Neither is going to be all constants because we ended up with a sphere and a cylinder. So one set of limits is going to vary no matter what we do, whichever coordinate system. Okay. So let's take this off because we're going to do a little bit of side work. All right. So first thing we need to think about is what our limits are going to look like and how we're going to convert that function. So there's something really cool that's going to happen here. It's going to help us out. And wait, what do you know about it? So what I want you to notice is rho. Remember that rho goes from the origin out to the edge, right? But our rho isn't going to start at the origin because we need that blank space, right? So it's going to do something like, it's going to pick up here and then go out to there, right? So depending on where I put this, there, right there. Can you see how the length of that changes? That tells me that the limits on rho cannot be constant. Now the outer limit's going to be a constant because the outer surface is a sphere. The inner one won't be because it's actually being made by the cylinder. So I already know if I'm doing rho first, I already know this is going to go out to rad 2. That's my upper limit on rho. We'll handle the x squared plus y squared and inside here in just a second because there's something I want to show you first. And it's dealing with this cylinder. So the equation of this cylinder is x squared plus y squared equals 1. We need to convert the cylinder into spherical coordinates. All right. So x is rho sine phi cosine theta. Y is rho sine phi sine theta. Okay, those are straight off the sheet. I'm not, that'd be coming off your note card, right, for the exam. So all I'm doing is our transformations, right? All right, we got to square all this stuff. So I got rho squared, sine squared phi, cosine squared theta, plus rho squared, sine squared phi, sine squared theta equals 1.
Just going to take the rho and sine.
I'm going to pull those out. I'm going to factor those guys out. So rho squared, sine squared phi times cosine squared theta plus sine squared theta equals 1. Here's our Pythagorean identity. So that equals 1. So what we're finding, two things. First off, x squared plus y squared simplifies down to rho squared sine squared phi, right? So when I'm going to convert this function, just because I don't have room to write it again, the x squared plus y squared for the function is rho squared sine squared phi. Then I've also got to put in the rho squared. Sorry, that looks more like a theta. Let's do that again. Phi sine phi. That's the one that's part of our dv. So this is from the function. This is from our dv. Yeah, you're going to end up with a rho to the fourth sine cubed phi when you simplify that. Now we got to keep going with this because this is going to give us our lower limit on rho. So I'm going to, that is equal to 1. I'm going to divide both sides by sine squared phi. So rho squared equals 1 over sine squared phi. Then I'll square root both sides. And finally, we get down to rho equals 1 over sine phi. That's what's going to allow rho to go along this vertical line right there. That is our lower limit, 1 over sine phi. And again, where did that come from? Well, that came from because the inner surface is x squared plus y squared equals 1. I transformed it into spherical and solved it for rho. So procedurally, it's actually just following those steps. And so now we've got our first set of limits. Rest is angles. Theta is easy, right? 0 to 2 pi is going to take this thing around. So really, the only other thing we need, we need phi to take this guy from there to there. Those intersection points. All right. So let's think about how we're going to figure out those intersection points. Well, we can do it in, let's do it in rectangular. It is where our cylinder hits our sphere. So it is where our x squared plus y squared equals 1 hits our sphere, which is x squared plus y squared plus z squared equals 2, right? That was the sphere. And we know that x squared plus y squared equals 1.
So 1 plus z squared.
Good. 1 plus z squared equals 2. So z equals square root of 1 or 1. So that tells me that this point right here, that is at, the height of that thing is 1, right? Everybody okay with that? Similarly, we know that this distance here is my drawing is obviously not going to be to scale. That distance there is the radius of our cylinder, right?
1.
So it's also 1. So now we can find this angle using right angle trig, right? We do the angle another way as opposed to the last one. Now, tangent of theta equals 1 means theta is once again a 45-degree angle. But I just want you to see, this is how we could have done it if it was some non-standard angle. We can do it for any situation. It's just an intersection of two surfaces, which makes this angle, once again, pi over 4. That makes this angle also pi over 4. Well, both limits can't be pi over 4, right? Well, we need this angle here. That's our lower limit. Let's keep this color. Our lower limit is pi over 4 on phi. So we're doing phi next. Our upper limit means, well, where are we going to end? We're going to go all the way to here. Well, if this is pi over 4 and this whole thing is pi minus pi over 4 is 3 pi over. And there is our upper limit on phi. So what phi is doing is it's taking rho and moving it along that piece of the sphere. And because our lower limit on rho varies, that's what keeps it straight here and gives us this crescent shape. Now we'll use theta to rotate it. And that's our 0 to 2. All three of those are going to give us the same answer. And if you know, I mean, it's a tough one to say which is going to be easier between these two. They're both, neither of these are going to be particularly nice. And that's because we were between two different systems, but both of these are going to be easier than rectangular, especially because they come out to be a single integral.